All right, so those inverse trig functions that we were working with in 5.6 carry right on into 5.7, and we're going to do integration. But what we're not going to see is integration of actual inverse trig functions. So if you have your antiderivative sheet that I handed out to you where you get to use it on the test, you might want to grab that out. Because the first thing we're going to do is we're going to actually fill in 3 antiderivatives. Now, these antiderivatives are actually going to result in arc trig functions. Okay? So the answer is going to be an inverse trig function we worked with. So as you're getting this out, some of you already have it, I want you to compare what's written right here to those derivatives that we got in the last section and tell me what you notice is different.
I have a question.
Yes?
Will you post a new set of that sheet with derivative sheet?
It's online.
Oh, it is?
It's already posted, so if you want to print out a clean one, do that. It's already there. Yeah. What do you notice is different about these 3 as compared to the 6 that we just looked at, the solutions for the arc, or the derivatives for the arc trig functions? These have a's in them, don't they? What did they have on the last one? They had 1s. So this is a more general case of what those actually gave us. Okay, so that's what you're seeing happen here. You're actually seeing this, you're going to see those arc trig functions, but you've got an a in it, which is actually really nice because that means you don't have to have 1 minus x squared and 1 plus x squared everywhere. You can have some other number in there, and these formulas will still work. Sound good? All right, so let's take a look at what these actually give us. All right, the first one is actually which one? Which one does it look like from before? Which trig function? Arc sine, and that is exactly what it is. This is arc sine. But it's not just arc sine of x, it's actually arc sine of x over a. So that's where you're seeing that a come into play. And then what? Plus c, don't forget those guys. What does the second one look like? It is arctangent. But it's not just arctangent of x. What do you think it is?
X over A.
It is x over a plus c. This one has one other feature. At the very front of it, you actually end up with a 1 over a as part of the antiderivative. That's actually going to happen, at least in part, because we don't have that radical in the denominator there.
Why do we have the 1 over A?
It's part of the formula. If you'll take a look, if you remember when we worked with the last problem, the one where we made the error in 5.6, remember we got a derivative of an inside function going on outside? That's part of why that's happening. Yeah.
How come we don't have it on the first?
It's a really good question, and I know that we've explored that once before because I had somebody ask, and I don't remember the answer to that.
Okay.
Yeah, I don't remember why it doesn't end up happening on that one, but I remember we double checked and for sure this is the correct formula. It actually just isn't present. Yeah. I think it has to do with how it reduces when you multiply something through. But I'd have to double check. Yeah. We will see it happen on the last one though. What's the last one? What does it look like?
Arcsecant.
It is arcsecant. And it has that 1 over a in front of it. And it's the arcsecant of absolute value of x actually over a. And then we have plus c at the end of it.
Why does this one have the absolute value?
You guys are asking great questions. I've never had anyone ask me that before. I'm not sure. I don't remember. I don't know that I've ever explored that one at all, actually, as to why that is what it is. Trying to think. It wouldn't be a domain issue.
I'm just curious because the sine has the square root also.
Yeah, it does.
So there's no reason why it made it.
I don't know, but you know what? I'll find out for you. If you'll remind me next time, I'll send. You know what? You know what I want you to do, Chelsea? I want you to send me an email
Okay.
and say, "Hey, remember I asked those questions?" And I will find out an answer for you.
Okay.
One way or another, I'll find you an answer. Okay, can we work with them without knowing the answer?
Yes.
All right, thanks. All right, we're going to take a look at these functions. We're taking some that look like them and some that maybe we will need to force them to look like them with some algebra. All right, so this one sort of looks like which one? It sort of looks like arctangent, right? I mean, it's not a carbon copy, they never are, but it has that sort of a feel to it where you've got something squared plus something else squared in the denominator, and in fact, you notice there's no square roots, so it can't be either of the other two, right? Okay. We need to identify a few things. Let's first identify the easy one. What is A in this problem?
4, 2 squared.
A is actually 2, because this piece in the formula is actually A squared. So where we see that 4 in the formula is actually an A squared. So the A would have been 2. Make sense? So you have to remember that your A is actually part of the formula. That formula itself, remember, oops, too far, has A squared in it. So whatever your value is that's added to x squared, the A is actually square root of it, not the A squared itself. Okay, so A is 2 in our problem. What else do you see that's different that doesn't allow us to directly use our formulas? The x minus 3. So what should that sort of beckon you to do? U substitution actually is what we want. Okay? So we're going to do U substitution. This is U is going to be equal to what? X minus 3. But the beauty is, what is du? It's 1. So my du is actually exactly dx. So there's not any replacement of any, sort of visible number that I have to work with here. That 1 is acting as the identity there. So I'm going to actually rewrite this so that it looks a bit more like what we actually need for our formula. I'm going to write this as 1 over 2 squared, just to remind ourselves. There it is. Just to remind ourselves that A value is 2. And then I've got that u squared now in the denominator, and my dx is equivalent to du and can be rewritten. Now this looks exactly like the formula. I mean, it's a carbon copy now, except that A is actually 2. So I can apply my formula. My formula says I should have, when I take the antiderivative, 1 over the A value, which is 2, times the arctangent of u over 2, and then plus c. But at the end of any problem that you've got a u in, that you introduced the u, you don't leave the u, right? We need to put it back in x's because it started out that way. So this should be 1/2 arctangent of x minus 3 over 2 plus c. Everybody good with that one? Okay, let's try another one. Which one does this most look like? Yes, it looks like arc sine, right? Because I've got the square root, but I don't have something outside of the square root, right? Yeah, so this one's arc sine. But I've got a lot of pieces here that don't look like that formula either. Let's start with what is A. What is A in this problem? 5. It is 5, right? Because you see the 25, so the A is actually going to be 5. Okay, good. What else? Let's see. I've got a tangent here. What am I going to do with that? I mean, I don't have a tangent in the original problem. U. I do. I need to do U, just like on the last one that we did on part A. So U is actually going to be tangent, isn't it? Not tangent squared. The squaring of this tangent right here, that's the x squared that's part of the arc sine formula that I need. So I don't need tangent squared. I just need tangent, because then I can replace that tangent with U, and the squared will still be there. Okay, so it still matches the formula I'm trying to use. All right, so this is U equals the tangent of x, and that's actually a really good thing, because what's du?
Secant squared of x.
Secant squared of x, and do you see that in your problem?
Yep.
Yep. So that entire numerator and then the dx on the end become du. So let me take a step to rewrite. This becomes 1 over the square root of 5 squared minus u squared over, and then times du at the end. All right, so what's the antiderivative? Arc sine of u over 5
Plus c.
plus c. Very nice. Last step. Yeah, this will be the arc sine of the tangent of x over 5 plus c. Maybe it's not as pretty as you wanted, but that is the solution. Okay, let's try another one. This one's actually a definite integral, right? We've got some limits of integration on this one. First, it's a matching game, right? Which formula will this match up to? Tangent. And the beauty on this one is that what is my a? That is 1, so that's actually very friendly. And then I need to figure out if I need to use substitution. Do I? Yeah, what would u be? I've heard 3 answers. So you guys listen, I'm going to tell you the answers I heard. I heard 2x, I heard e to the 2x, and I heard e to the x. It is e to the x, Erica. Do you know why? I need the square to still be part of the formula when I'm done with u in it, right? I need this formula to have u squared in order to use that antiderivative I'm trying to use. So this will be just e to the x. So that my e to the x gets replaced. Now, some of you might be a little bit bothered by how this looks. Remember, this is just e to the x squared, because that's what e to the 2x is. Another way of writing it. So that's where you're seeing that e to the x is u, and that squared is still part of the problem. And the wonderful thing is, what is du? E to the x, is that in my problem?
Yes.
You bet it is. All right, so I'm going to take this particular formula. I'm going to rewrite it without the limits of integration. I'm not putting the 0 and the ln 5 in. Why? Because that's not, those numbers apply to x, and my problem is not going to be in x in this particular step. It's going to be in u. So I'm going to leave them off. So on the top, I have du, or 1, with a du at the end. And on the bottom, I have 1 plus u squared. So far, so good? All right. That is actually a very nice formula. In fact, if you actually looked back at when we defined the arctangent, that's exactly the arctangent formula. Okay? Because if I take my generic ones that I gave you in this section, the very first part of this section, with the a being 1, I'm going to get 1 over 1 arctangent of u over 1 plus c. I don't need the plus c on this one, though, because it's a definite integral. So this is actually just the arctangent of u. Yes, Chelsea?
On like our homework or the test, that I wrote the limits, would you have off that?
Yes.
Okay.
If you write them too soon.
Okay.
Because wherever you write them, it should apply to whatever variable they're used with. And so right now, they're not used with u, so they shouldn't be written with u.
Okay.
But I'm about to write them, because this will actually now be the arctangent of e to the x, right? And then I can evaluate that at the natural log of 5 and at 0. So I'm going to come back over here to do that. So this is the arctangent of what? Which one do I plug in first?
Natural log 5.
The natural log 5, the one that's on top. So this is e to the ln 5 minus the arctangent of e to the 0. Both of which simplify. I have space over here. Okay, so what does e to the ln 5 simplify to?
5.
That's 5. What does e to the 0 simplify to? 1. So this is arctan 1. And you do have to simplify the arctangent of 1, because that's on the unit circle. Okay? Arctangent of 5 isn't, so it can be left as arctangent of 5. But the arctangent of 1 is on your unit circle. So let's take a moment, we talked about this last class, and think about our unit circle. Where is tangent, well, first of all, where is arctangent allowed to be considered? 1 and 4. Good. 1 and 4. In which one of them is arctangent positive? Positive is 1, right? Okay, so this 1 right here is positive. So we're going to be in quadrant 1. So in quadrant, it's a terrible arrow. Let's try that again. In quadrant 1, what angle gives me a tangent value, right? This is equivalent to saying the tangent of theta equals 1. What angle gives me a tangent value that's 1? In the first quadrant, yeah. Which one? Which angle measure? It's 45 degrees, which is pi over 4. So this is happening at pi over 4. If you'll remember, basically what's happening is that the x value and the y value are the same. And so when I take the ratio of y over x or sine over cosine, I actually get the value of 1. So this is equal to the arctangent of 5 minus 1. 1, sorry, 1. I was talking about 1 from 4. Minus pi over 4. There we go. Look good? Look okay anyway. All right, one more problem. This one is a little different. In fact, the directions even tell you you've got something else going on. What do the directions have in them that's different? Complete the square. Do you remember that concept? Like from, I don't know, it's probably been quite a while ago that you've done much with completing the square. You may have seen it briefly in Calc 1. But you're going to definitely need it. It's definitely one of the tools for integration that's necessary for us, okay? Now, we're going to see, we see that square root with that variable x in the denominator. So that should incline us to think, oh, I'm thinking about arc sine, right? Make sense? Okay, so this looks sort of like I might need to do something with arc sine. But in arc sine, I should just have a constant squared and a variable squared. And I've got stuff that's not even squared right now, that's got a linear term of x in it. And completing the square actually allows us to change this or manipulate this so that we can use that arc sine formula. Okay? So the first thing we're going to do is we're going to take a look at this and we're going to talk about the completing the square. And we're going to be completing the square on the negative x squared plus the 4x. And in order to do that, I don't want to deal with the negative at the beginning. That's not a helpful feature. So I'm going to factor anything that makes this not x squared out. So if there had been a 2 there, I'd factor the 2 out. If there had been a negative 7 there, I'd factor the negative 7 out. This one just has a negative, so I'm factoring the negative out.